Okay, good morning, everybody. So I want to just take say some words about the rest of the class. This week we're going to cover convolutional neural networks, and I believe that we won't cover object detection, so we will do this next week. And recurrent neural networks we will cover on Thursday. And I'm not going to have class on the last week, like the week when the mid finals begin. So next week will be our last week. Am I correct? Yeah. So and we won't have time to cover sequence-to-sequence attention and transformers models. But if you will, yep.
Actually, it's an action. It's not. I mean, it's. I guess technically when it's like measurement, like cross validation, but it's also like mainly because I'm working on another project that I had to do some like
Okay.
little machine that do some kind of do some height parameters or feature height parameters or anything that like I don't know whether or not it's like conflict of interest.
No, it's fine.
I mean, like with the team, I mean, like I have another class.
Yeah, you can use any assignment from this class for another class. So yes, but if you're interested in these topics, there will be class on large language models, and uh, it's under special topics. 59539, of course, where we actually cover this attention transformer models. So, okay, this is the plan for the rest of the class. And I will introduce project when we'll cover this convolutional architectures next time, because the project is related to convolutional neural networks. So today we will finish our batch normalization and dropout and begin working with convolutional neural networks. So we stopped on dropout last time, and you remember that the formula for dropout layer was as follows: the element of the previous layer times a random number which takes values 0 or 1s. So let's see. Yep.
Is there any benefit to randomly initializing the weights for the network over just putting them to 0 or making them?
Yes, I will answer this question when we will cover batch normalization. So before batch normalization, just before batch normalization, it was really important how to initialize neural networks, and because they were not stable for training, but when batch normalization was introduced, about this after dropout, it's now no longer a problem how to initialize this. Well, of course, there are some observations which layers is better to initialize by zeros, which layers initialized by random numbers, but the normalization helps. So the first technique of normalization that we started last time was dropout. Yes, so this was a random number with some probability p. And as you remember, it worked as follows. we had a layer A, for example, and dropout layer just copied these numbers, or we also call them neurons. If y was equal to 1, for example, if y was equal to 1, it just copied these values. If y was 0, it just skipped these values multiplied by 0. So so this is how this dropout layer works. And yes, we didn't, let's look at the expectation of this output from dropout. Because now we have a random variable y, we can calculate the expected value, expectation I times yi. So what is the random number? What is a constant for this product? Because the constant we can just take outside of the expected value. What is the constant, a or y? Y is a random variable that has Bernoulli distribution. So it means that a is a constant, so we can take out the constant. And what is the expected value of Bernoulli random variable? So yi takes values 0 with probability p and 1 with probability 1 minus p. So what is the expected value of this random variable? Expected value is the product of the value times probability plus value times probability and so on. Yes,
Is it 1 minus p?
1 minus p, because we multiply 1 times probability plus 0 times probability. So it will be 8 times 1 minus p. And here is a little problem, because when we calculate the forward paths of path, I think it doesn't matter. When we pass our neural networks in forward mode, we want to get the output from this layer unchanged. We want to get a instead of a multiplied by some constants. So to fix this problem, instead of multiplying by 1, we can multiply by 1 over 1 minus. So in practice, to get, of course, you could fix this after the output from dropout, but it's easier in practice, just multiply instead of multiplying by 1, to multiply by this fraction. And then the expected value will be 1. Because this time, this probability will be 1. So in practice, yeah, we will use slightly modified it's Bernoulli this random variable that takes values 0 and 1 over 1 minus probability. Because if we use this yeah, for example, if p is 0.5, then this number will be 2. So we will have 2 times a, and if we multiply times 0.5, they will cancel out and we will get just a. So this is how dropout works. So in forward mode, we multiply by random number during train mode. In evaluation mode, we don't drop any numbers. In evaluation mode, we use y equals to 1. We use y equals to 1. So we don't just apply identity transform. Okay, so this is the first layer which behaves differently in training and evaluation mode. The next layer which performs this normalization is called batch norm. Batch normalization. And do you remember when we talked about linear regression, we normalized our features, like we applied min-max scalar, we applied standard scalar. So do you remember what was the reason to normalize the features for linear model?
In the case that there is some sort of feature that is technically trivial, such as the amount of floors on a building, but you also have a bunch of other important features that have relatively small values. Like some domain is 0 and 1. You use it, and when you're using it on some model on scale, you haven't shown it's more likely than not that your model is gonna heavily depend, the results of the model are heavily dependent on like that very trivial thing that has a really huge domain.
I'm talking about feature importance, maybe. Like when we look at the weights and then to answer the question which feature is more important, we should normalize these features. Or you're talking about
this
just in general.
Fine, this
Because I think your comment is more related to feature importance, which feature we should take into account and which feature we can eliminate, maybe. Yes, or
I was just trying to make an example.
yeah, but it's a good example. Yes.
Are you selecting? If you already have like a select set of features that are all equally important, but one has just a higher maximum.
Yeah,
lower
magnitude.
And suddenly like the model, it may more or less would just be better off with one feature.
Yes, but it's more related to feature importance. But if we are interested in the training process for stability of training, it also helps. Yes.
We use the standard scalar because sometimes some features are like in the hundreds and some features are like
Yes.
decimal, so you want to do all these things.
And how it results in the loss function landscape? Do you remember? If we have features in different scales, the loss function will be kind of extended along this direction. And as you remember, if we have loss function looking like this, when we start gradient descent, it goes in the normal direction. So we will can always move in this normal direction, and we will perform a lot of steps. Or if we take a gradient along which direction? Maybe this direction. Then we can get a very large steps. So the normalization in linear models, when we have quadratic loss function, resulted in more symmetric shape of this loss function. And in more symmetric shape, we converge much faster. So in neural networks, what do you think? Neural networks loss functions, do they have one minimum or multiple minima? Minimum? No. Minima. Yes. So what do you think? In other words, are neural networks convex loss function? Are they convex or not convex? So you remember convex functions, they look like this. They have one minimum, and non-convex functions, they can look like this and have, for example, multiple minima. So what do you think? Yep.
If neural networks represent any sort of arbitrary distribution, and they're used that way, then there probably is like a distribution function within there that does that is not convex.
Well, maybe it's hard to answer this question without some examples. But if you take, for example, a plot sigmoid function of sigmoid function, and neural networks is just the stack of linear layers and activations. So we apply one nonlinear function, then linear layer, then another nonlinear function. So it's a combination of nonlinear functions. And if you just plot sigmoid of, for example, the sum of two sigmoids, you will see that it will have two minimum. So yes, in general, neural networks are not convex. And this is why when we train them, the loss is oscillating because you can end up in one minimum, then when you perform the gradient descent step, you can end up in another minimum. So the loss function is oscillating. But gradient descent helps actually to not to stack in one minimum. It helps to jump into other, maybe better minimum. Okay, so I think it was the question for the homework, which was due to yesterday, no? Or maybe for the next homework. There is a question about if what do you think if the loss function for neural network is convex or not? So it's not. Now we have a neural network. In neural network, we have multiple layers instead of so it's not enough just to normalize input features, because if we normalize input features, it will help only for the first layer. But if we want to get similar magnitude on some hidden layer and unit variance for a hidden layer, then we can apply the following idea. So for example, we have input X, and this will be X batch norm. So for one, it can be a hidden layer X. Typically, we denote by H, but it doesn't matter, I believe. We can calculate mean. So you remember we have endpoints in the inputs to our neural network. So on this layer, we will have also some points xi, with coordinates, let's say j, and I will go from 1 to the batch size, because the input in our neural network is a batch, not the entire data set. Then we can compute the mean and variance for this batch. So we can compute two numbers, mu, for every component, for every coordinate, so mu j. It will be 1 over batch size, sum over all the points from 1 to batch size. And we will, bless you, and we will take the average only over one coordinate, over j equals 1 over j equals 2. So we will calculate the mean over the batch for every component. Then we can compute the variance. Well, typically we use standard deviation, the square root of variance. Also for every component. Or 1 over batch size. And formula for variance is x I j coordinate minus mean. And after that, the output from batch normalization layer, x jth component for point with index I batch norm, will be the kind of standard scalar, but for this current batch. So it will be x for every point I, jth component minus mean over the variance, standard deviation. So sigma without square. Okay, so yes, because we don't have access to the entire data set, we can compute mean and variance for the entire data set. But we can compute this statistics for a batch. So that's why it's called batch normalization. So it's fine. So this is how we will calculate, normalize our batch components during training. Now, what about inference? Because when we want to apply our model to predict something, to evaluate on the test data, which parameter? Oh, actually, it's not the end of the. It's not the. Oh, sorry, it's not the final formula. So the final formula, there are also two additional parameters. Okay, sorry. Before going to evaluation, the final formula is okay. Let's denote this by x prime, and final formula actually includes two extra parameters. So x batch norm, x batch norm, also we'll apply a linear function to this normalized function with some parameters gamma. And plus bias delta. Okay, so I'm sorry, I have forgotten about this. So in addition to normalization, which norm layer applies also a linear function. So it multiplies these normalized values by some coefficient gamma plus delta. And these parameters, they have gradients. They are trained during training with bits of our neural network. But mu and sigma, these are costs because they are calculated from data. So when we'll apply our Bayesian normalization layer in evaluation mode, gamma and delta we will have from our parameters of our neural network. But how to get mu and sigma? So before answering this question, let's think about why, in addition to normalization, we apply also linear combination, linear function. And the answer is that Bayesian normalization layer, we want that Bayesian normalization layer can perform identity transform. Because maybe we don't need to change anything in our layer S. So we want to have at least that a possibility that Bayesian normalization layer can return X unchanged. So this additional linear function helps to perform the identity transform. Because if you use instead of gamma, this variance sigma, it will cancel out, and instead of delta mu over sigma, you will get just X, unchanged X from Bayesian normalization layer. So to make sure that our neural network can perform identity transform, they added these also two parameters. Now, evaluation. In evaluation, these parameters, gamma and delta, we have from our neural network. What about mu and sigma? Do you have any ideas how to keep track of these parameters? Because mu and sigma we calculate for every batch separately. And which parameters for which batch to use during evaluation, it's not clear because we don't know that which data our test data are similar to batch 1 or to batch 2 or so. Do you remember last time we talked about moving average, the exponential smoothing, when we kind of aggregated the loss function? Also, we aggregated some parameters in Adam optimizer. So here they use the same idea. They just keep this exponential smoothing or moving average. Use some parameter alpha times, for example, mu j on the previous step plus 1 minus alpha times mu on the current for the current batch. And store this moving average for mu and c. So, and during evaluation, they use these two numbers to perform the normalization. Does that make sense? So that's why this is another layer which performs differently during training and during evaluation. Okay, now let's talk about the initialization. There was a question about initialization. Again, the initialization of neural networks was crucial before people introduced batch normalization, and it was really important question. And of course, it's maybe not a good idea to initialize everything by zeros. So there were two popular initializations. Initialization of neural network. Again, nowadays we don't care because this torch library has built-in initialization, and batch norm takes care of the similar magnitude of weights on any layer. No, but typically we don't apply batch normalization for every layer, even though it looks like it's a good idea. But because it has so many parameters, additional parameters, gamma, delta, moving average for mu, and sigma for every component, it takes a lot of space. And in practice, in neural networks, maybe two batch normalization layers are used, even if you have maybe 20 or 30 layers, batch normalization is not used for every layer. So initialization. There are two initializations here and Javier. Yeah. So if we look at one layer, we have some inputs and we have some outputs. So input, let's call it maybe layer H input, and H output. And as you remember, we used this formula many times. The variance of the sum. The variance of the sum, it was proportional to 1 over n. As you remember, the variance of the sum. Variance of the sum is the sum of variances. If we assume independent data, so the variances. And if we have here normalization 1 over n, then it goes outside as 1 over n squared. And if we assume equal variances, it will be n times variance, and will cancel out, and the result will have 1 over n times variance. So the idea of initialization was to keep the same magnitude of these random numbers along every layer. So if our layer has had the size, for example, D, then we could initialize our points, our neurons by weights like epsilon over square root of D, because the standard deviation is the square root of variance. And if the variance has magnitude 1 over D, the standard deviation will have magnitude 1 over square root of D, SQRT of D, where epsilon is just a random number from standard normal distribution. Javier initialization takes into account both input layer and output layer. In Javier, so where D is the dimension of input layer. In Javier initialization, we use square root of the sum of input layer and output layer. So it will result in smaller magnitude of random initialization. So nowadays, if you look at, for example, linear layer, yeah, you will find this information. Initialization and well, instead of normal distribution, they use uniform distribution just on the interval, but the interval is again between square root of, well, actually, in my formula, sorry, there should be two. There should be also factor 2. Well, it's just a factor, but still. So, yeah, in this case, they use the uniform distribution, but again, between 1 over square root of the size of input features, so negative, and plus square root of 1 over input size. So it means that they use here initialization. But you can use your own initialization. But typically we don't bother ourselves about this because with Bayesian normalization we can normalize these weights inside our neural network with Bayesian normalization layer. Okay, and dropout also performs normalization. I have one example. I don't want to run this code. I just want to show how we apply these layers, Bayesian norm and dropout, and go and move to the convolutional neural networks. So I prepared this example for last week, but we didn't have time. So this is the familiar data set with California housing prices. And I decided to use this example just to show how apply neural networks for table data and also to show that the result, the metric, for example, R squared will be worse than in case of gradient boosting. So The problem with this data set is that we have not numerical features. And I created this data set here and created manually one-hot encoder. So I created a vector of size of 5, the number of different classes in this last column, and then initialized it by zeros, and then changed the component corresponding to each class by 1. And as the result, I have what's that? Is it batch size? Oh no, it's the number of features, 12 features. So in addition to these numbers, I think, I don't remember, maybe several columns were dropped. 1, 2, 3, 4, 5, 6, 7, 8. We also added this one-hot encoder feature, so that's why we have 12 features. And finally, the model. So the first model is linear regression, and the second model uses batch normalization and dropout. So typically, we apply dropout after activation. And let's see, I don't have this example. So if we want to apply batch normalization, we apply this so there is no rule if we want to apply batch normalization before dropout or after dropout, but typically we apply batch normalization before activation and dropout after activation. And there is just training. And believe me, if you calculate the error, the R-squared, for example, metric, it will be worse than for gradient boosting. Okay, now let's move on our new topic, convolutional neural networks. Or how to work with images without unrolling them in a long sequence, which is a little bit strange. So, and I will upload the image which is used in any, which was used actually, which was used in any paper on computer vision and in any course on computer vision, the image of Lena. But last year, I looked at one conference rules, and or maybe it was journal, and it was written that please don't use this image of Lena because it violates some like privacy rules. So let's use pill library because it's a GIF image, and if I upload this image and plot it, it will look weird. It will look weird because, as you might know, the GIF format, it doesn't represent the magnitude, the intensity of colors. It just codes the colors themselves. Like each color is coded by one number. One, I don't remember, know exactly, but let's say 2 corresponds to pink, 3 corresponds to red, and so on. So that's why it looks weird. So you remember we should use, for example, convert to L to get image in grayscale. And then it will look as it should look like. So in conventional computer vision, before neural networks, we could increase the brightness of the image. We could add noise to make it to add blur into image, remove this blur. So how it was done? It was done with filters, so-called filters. For example, uh, I can create a tensor of this size 3 by 3 with these numbers, ones in the first column, zeros in the second, and negative ones in the second. And multiply by the image. So we will take the image and then multiply on the 3 by 3 pixels region, which is called patch, by this filter. So let's say we have some values for pixels, for example, x 1, x12, x13, then second line x21, x22, x23, and so on. x31, x32, x33. And then we multiply these numbers by the filter by a matrix 3 by 3. It means that we will take x11 multiplied by negative by 1, x 12 will multiply by 0, and x13 will be multiplied by negative 1, and then we will add them together. So if we add, but because we have negative, we will actually subtract the third column from the first column. What do you think? Which pattern we will get? The vertical or horizontal? So it's called a differentiable filter because the difference looks like the derivative, because in derivative we use delta x or delta y or delta x. What do you think if we apply this filter to our image, which patterns it will emphasize? Horizontal or vertical boundaries of or shapes? What do you think? Well, let's apply it. So this operation is called convolution. So I will apply convolution with this filter to our image. And this is how the result will look like. So what do you see, which patterns it emphasizes, vertical or horizontal? I think it's straightforward. We take a pixel, like a column of pixels, and subtract from another column of pixels. So we get the vertical we change the vertical brightness. So it will emphasize the vertical lines. If we apply filter with ones in rows and negative ones in row, it will emphasize the horizontal patterns. Here is just an example that, yes, so this is how it will look like. And by the way, yeah, you can indicate the boundaries for your image, like from 0 to 255, and you could see that the image looked a little bit different from the top one. So this is the result. Of applying this convolution. So you can see that it kind of emphasizes the boundaries of the objects. And in this case, the vertical boundaries. Okay, now let's talk about a more recent approach to image processing. And more recent idea is why we should use some filters with fixed numbers. Maybe we can learn these filters. We can learn these numbers in these filters. And this idea brought to the convolutional neural networks. Let me open my presentation. Okay, so as you remember, we had a theorem that arbitrary function can be approximated as a sum of sigmoid functions. So this is just an example of paper that tried to use one hidden layer neural network with sigmoid functions on NIST data set. On NIST or yes, handwritten digits on NIST data set. And they actually got the same result as convolutional neural networks. But I think it just was a joke paper because to get the same result as convolutional neural networks, we had to use this dimension of the hidden layer. And I even can't read this number. What is that? So this is, so in other words, we can apply convolutional neural network with maybe hundreds of parameters, and we will get the same result if we apply a linear layer on images, but with this number of parameters. I just want to emphasize that it's a good idea to use convolutional neural networks for images instead of feed-forward neural networks. So the idea of these filters that we should learn some like line patterns from our images was appeared in the experiments on the cats, unarrested cats. So without anesthesia, they implanted the electrode into cat's brain, and I think it's impossible to perform these experiments nowadays. But at that time, they tried to show different patterns to the cat and detect signals. Unfortunately, doesn't matter which patterns or images they showed, there was no any signal from this electron. So, and as the legend says that by mistake they dropped a piece of paper, and then they got the signal from this electrode, and then they realized that they should demonstrate the straight lines, kind of the edge of the paper, a sheet of paper. And yeah, so this paper provides these experimental results about how the signal from the pet's brain depends on the rotation of this linear pattern. So, yeah, on this image, they didn't perform this experiment on Liana, but as I mentioned, you will see this image in any textbook or earlier conference papers on vision. So here's the idea of how we can apply fixed filters. In this case, this filter kind of adds sharpness to the image. So it adds this kind of averaging filter with subtracts with some constant. So this is this averaging filter. And after this operation, we get a sharper image. But it's all the old conventional computer vision. So nowadays we use the learnable filters. Okay, so this is the idea of convolution. We multiply the stage of our image by a filter and add up the result. So in this case, we multiply 4 by 1, bless you, so 5 by 1 and 2 by 1. And it's easier to subtract. 4 minus 2 will be 2, 5 minus 2 will be 3, so 2 plus 5, 3, and 2 minus 5, negative 3. So we'll get 5 minus 3, 2. So the result of one convolution is just one number. Then we shift our frame by 1 and perform the same operation. So from this region, we will get again one number. And we will stop when our frame actually will reach the end of the image. So what should be the shape of the output image? Well, I'm saying image, but the output won't be an image, and they call this feature maps, because we will get some features from each. But sometimes I will call the resulted image. So what will be the size? If we have 1, 2, 3, 4, 5, 6 length of 6 here, how many frames we can apply? We can apply 1 frame, 2, 3, and 4. And after that, we don't have any room to move further. So the output shape will be 4 by 4. So our original image was 6 by 6. If we apply filter 3 by 3, the output shape will be 4 by 4. What if we apply filter 5 by 5? I think we will have this example later. Okay. I don't see this. So what if we apply filter 5 by 5, for example? Or if we apply filter 5 by 5, so it will take this part it will take this part of image. And what will be the output shape if we use filter 5 by 5? It will be, yeah, you can speak those. It will be 2 by 2, yes, because we can shift this filter only by one more. And you can actually figure out the general formula that relates the input shape of image and output shape of image or feature map if you know the size of the convolution filter. So, for example, I believe I have this example later. But we can derive this formula. So, for example, if the size of filter was 3, it was 6 minus 3. Let's see. So we can shift by 1, 2, 3, 4, and in the end, in the last filter application, we have 3 minus 1 left columns. 3 minus 1 left columns. So it will be minus 3 minus 1. And the result will be 4. And so in general, yep, yes.
The difference between a convolutional and traditional neural network is that the convolutional one is just really the dimensions of the knowledge layer being going from.
So the convolutional layer is applied on net, it's on 2-dimensional. The previous feed-forward method we applied on 1-dimensional layer. So this is the main difference.
So is that just by extension how each neuron technique is designed in a sense as a sort of product of the.
Yes, so this is called, so in literature we'll think sometimes this dot pair inductive bias. So this is our, like in paper, this is our inductive bias. So by inductive bias, people mean some assumptions. So for images, it's reasonable to treat the image as this two-dimensional. If we have a colored image, then we have also channels, then it's 3-dimensional arrays. Instead of unrolling this into a long vector. Because in image, it's the reasonable assumption is that neighboring pixels, they kind of somehow related to each other. And if we unroll this, then we will get like pixels from the lower row very far away from pixels from the previous row. And so it's called in literature inductive bias. So inductive bias for images is that we should use convolution filters, not the linear layers. Inductive bias, for example, for text, for speech, is that we should use recurrence or transformers, so architectures that work with sequences. So, yes, and as Jason correctly asked about the input shape now is 2-dimensional instead of 1-dimensional, and the output shape will be 2-dimensional. Okay, let's move forward. So another notion in neural networks is called receptive field. In other words, if you think about one filter. So if we apply one filter that to this red pixel, it will capture the information from these neighboring filter pixels. So receptive field here will be 3 by 3. But if we apply twice the convolution layer, so we apply filter 3 by 3 one time, and then we apply the second time. Then, from the first layer, our receptive field will be 3 by 3, and it will affect this purple pixel. But after applying the first convolution layer, we kind of will collapse all this 3 by 3 region into one pixel. So if we apply again 3 by 3 convolution layer, we will take into consideration the neighborhood of this purple filter, and the resulted receptive field will be 5 by 5. So it's another idea that if we apply several convolution layers, we can capture kind of larger region of the image. Yes?
So this is with this, and this is simply just with this, with the filter of the same dimension applied across numerous iterations.
So what is the difference? So there are two options. We can apply the filter 5 by 5 to the original image. If I apply filter 5 by 5 to the original image, what will be the number of parameters? It will be the 25, 5 by 5. 25 parameters. What if we apply a filter 3 by 3 by 2 times? What will be the number of parameters? It will be 9 times 2, which is 18. So it will decrease the number of parameters. So when we will talk about architectures, nobody nowadays applies just 1 or 2 convolution layers with large filter to capture like large region information about large region in the image, but we apply multiple layers with small filters, but the result will be the same. Because if we apply twice the filter of shape 3 by 3, we will actually take into consideration also the neighbors of the previous. Okay, what else? What else? Stride. Okay. We will talk about size of filter. There is another parameter, stride. The stride is the shift. Typically, by default in NN torsion and layer, the stride is 1, so we should by 1 pixel. But you can indicate stride 2, then you will shift your frame by 2 pixels every time, and it will result in a smaller output shape. Because now we apply this filter once, twice, and that's it, because we can shift by 2 anymore this filter. So the output shape will be 2 by 2. So if you have, for example, very large images, it's a good idea to use stride to compress this information. Also, there is idea of dilated convolution. So you can apply this filter, but not to the part 3 by 3, but to kind of 3 by 3 matrix, but with skipped rows and lines. So this is called dilated convolution. It also reduces the size of image. And yeah, the resulted image should be 2 by 2. It's around yellow matrix. And the last parameter in convolutional neural networks is fading. What if we don't want to change the image shape? What if we want to keep the shape 6 by 6? The answer is add extra dummy columns and rows, because you remember the size of our image was reduced by 2. If we add 2 columns and rows, the resultant image will have the same shape. So in this case, if we will apply 1, 2, 3, 4, 5, 6, and we will get the output shape again. The yellow image has incorrect shape. The output shape will be 6 by 6. So this is the idea of plating. If we don't want to change the image dimension. And the last, I believe, operation, yes, the last operation on images is called pooling. So max pooling, so we split our image into batches, or in this case into 4. And we take just the maximum value in every batch. So from this image 4 by 4, we will get image 2 by 2 with numbers that are maximum values in every block. The other option is to use average pooling. So instead of maximum number, we will take average of these numbers, and we will get smaller matrix. And if we combine this convolution with max pooling or average pooling, we will get an interesting observation that neural networks, convolution layers are shift invariant. It means that if you have image of cat in the center or in the corner, the convolution layer actually will be able to extract the important features for classification of this image. And this is just a simple example. For example, we have 2 patterns, the same patterns on our image in these corners. If we apply convolution filter that has the same pattern, so it will emphasize this diagonal. So we will get, for the first pixel, we will get 2. If we assume that there are zeros on this empty space, then for this pixel, when we convolve with red filter, we will get 1. If we look at and if we take a max pooling after that, we will get just 2. And if we apply this operation for this corner, we will get exactly the same number. So it's kind of illustration of this idea that if we choose a correct filter and can apply 2 operations, convolution with this filter and max pooling, we will preserve the information on our image. Okay, I think we should stop here yeah, for today. And yeah, let's continue next time. The code examples. for your last homework. Let me stop recording.